Hi, my name is Matt Mogensen, and with my partner Jason Spyres for our final project in decision making and uncertainty, we wanted to design a sequential learning problem with a very large space that required online planning. We wanted a game that would be fun, and we thought that the game of Connect 4 by Hasbro Gaming would be an interesting one to look at. So the basics are there are 42 playable positions in a 6x7 grid. Players select one of the 7 columns, and the first player to line up for their own colors, either horizontally, vertically, or diagonally, wins the game. The state space is such that it blows up exponentially. For example, after 2 turns, there are already 49 possible states. After 18 turns, assuming no one has won, there are over 1.7 billion possible states. So our approach with online planning allows us to look at a much smaller subset of the reachable state space in order to pick our next action. So the approach we used was to implement a forward search with 2 depth look ahead using a local heuristic reward function.
I'm now going to take a minute to explain what our overall strategy was and how we went about implementing our heuristic to tell the AI how to make a decision. First thing we needed to do is we needed to win. It looks to see if there's any 3 of its own color lined up and could it place a 4th and win the game. If so, we weighted this with a high enough reward that it would always choose this action. If that action was unavailable, its next choice would look to its opponent's colors and see if they had 3 lined up. And then it would choose to block, sustaining its life into the next turn. Next, it would look for various structures, as we explained in the slides, where it would increase its likelihood of coming to a winnable state space. These structures include having 2 of its own color lined up with 2 empty spots on each of its sides, allowing it to have a Connect 4 in the future state spaces. After going through all of these structures or preventing its opponents from having these similar structures, then would assign a random move if there was no other move that it should do with inside the heuristic.
So the idea is that we calculate the reward function for each slot. And then we want to maximize the total forward search reward using the look ahead up to a depth of 2. And the following assumptions are made. We assume that the opponent will play the same strategy as the computer. We also assume that the human player will play in certain slots with a probability that's actually proportionate to their expected reward. So we assume that if the human player can win by playing in a certain slot, they're going to play in that slot with probability 1. Finally, for our look ahead function with depth 2, the total expected utility for each action is equal to the reward for that state in action minus some discounted expected reward for what the human will play in the next turn. Now, we'd like to point you to several weaknesses of our approach. One of them being that we chose to use an online approximation strategy versus an offline exact strategy due to the size of the state space. And 2, we could have implemented a larger depth in the look ahead, where we would consider not only our move and the opponent's response, but our follow-on move and the opponent's follow-on response, and so on.
In order to get metrics on the efficiency of our algorithm, we created 3 separate opponents. One would act randomly, regardless of what the other player did. When we ran this with 1,000 games, our algorithm won 955 of the games and lost 32, with 13 resulting in a tie. The greedy opponent simply looked at the situation, the state space it was currently in, and made the best decision of, can I win the game or can I prevent a loss? We won 685 games, we lost 113 games, and we resulted in a tie for 202 games. Finally, we did 1,000 games with a 1-depth opponent. We still won 432 games, lost 322 games, and 246 games resulted in a tie.
We're now going to demonstrate the computer AI playing against a random opponent to give you an idea of how this works. So the computer is in green in this case, and the opponent is in red. And right now it's just cycling through games, and when someone wins, it will display that win, and when someone loses, it will display that loss. So far the computer, for example, has won all the games playing against a random opponent.